This is example 5-9, enthalpy in an air duct. So we're given this circular air duct here, given the diameter of 200 millimeters, and we're given the inlet pressure and inlet temperature and even the velocity. And then we're told that farther down we have an exhaust system that increases the velocity at B to 25 meters per second. Now this exhaust system basically acts like a pump in our system, so we can write our energy equation with that way. Says there's no heat transfer through our pipe, so that will simplify it a little bit for us. All right, so with that, of course, air is a compressible flow, so we'll have to use the compressible version of our energy equation. So let's write this down just so we have it. So we have Q in, right? That'd be the heat transfer plus any energy added by a pump minus any energy that a turbine might be taking out. And all that is equal to then the enthalpy at the outlet point plus V out squared over 2 plus G times Z out. And let's write the rest on the second line here. Minus enthalpy at the inlet point plus V in squared over 2 plus G times Z in, and all of that times the mass flow rate. All right, so of course here we're given that A is in, B is out, so we can base everything on that. Let's do the easy one first, the datum. We can put the datum at the center line of the pipe. That would mean that the elevations are 0 on both sides. So datum at center line of pipe, which means ZA equal to ZB equal to 0. We don't have any turbines. No turbine, so W dot turbine equal to 0. We're also told that there's no heat being added. No heat added, which means our Q in is equal to 0. And then we know we have an exhaust system. So we can say our pump, our power, our energy in the pump is going to be equal to 2 kilowatts. So 2 times 10 to the 3, and we'll rewrite that as Newton times meters per second. Maybe we'll need it that way. All right, so we have all of that information. What else do we need? Well, so that means we've taken care of the first 3 up here. We've taken care of the Z out and the Z in. We are given the velocities, V in and V out. So now what else are we looking for? Well, we're looking for, we want to have the change in enthalpy, so we can just have H out minus H in, so that's fine. The last thing we need is our mass flow rate, our m dot. So mass rate we know m dot is just rho A times VA times AA. Now VA and AA are given to us, and we're given the pressure and the temperature and that it's air, so we can use ideal gas law to figure out what the rho A is. So we can say PA is equal to rho A times R times T. that means rho A is just P A over R times T. I guess we can put a TA in there too if we want to. So we can plug that back into our mass rate. M dot is then PA over R times TA times VA, and then the area here is pi over 4 times dA squared. All right, I think we have all those values, so let's plug them in. Our P at the entry point was 180 kilopascals. So that'd be 180 times 10 to the 3 Newton per meter squared. R for air is 286.9 Newton times meter divided by kilogram times Kelvin. Right, joule is Newton per meter. And then that would be our R. Our T would be, let's see, 15 degrees. And we have to add 273, so it'll be 15 plus 273. Result is going to be Kelvin. We're given the velocity at 10 meters per second, and then our area, so pi over 4 times diameter of the pipe is 200 millimeters, so 0.2 meter squared. And that gives us 0.684383 kilograms per second is what we want to get. Let's see if we actually get that. So we'll get cubic meters back here. That cancels out with the cubic meters that we get from this, right? It's squared and that one there, so it goes down. The newtons cancel out. Kilograms goes on top. The K's cancel out, and we have the S here. Okay, we get the right values. All right, so that plug all our stuff back into our equation, right? Then we can say, we said there's no heat gains or losses, so 0 plus power of the pump, or in this case, energy of the pump, nothing from turbines, and that is equal to HB, right? That's the enthalpy at B. VB squared over G, over 2, different option, different version, no elevation, minus HA plus VA squared over 2, and again, no elevation, all of that times M dot. All right, so what we want to have, we want to find the change in enthalpy, right? So we want to solve all this for HB minus HA. So we'll start out by just dividing by M dot. So on the one side, we'd have W dot pump divided by M dot is equal to everything here. We can get rid of the inside brackets there. So we'd have HB plus VB squared over 2 minus HA, and then be careful that we put a minus here, minus VA squared over 2. And of course we can solve that for HB minus HA, right? So we can say based on that we get HB minus HA would just then be equal to the energy from the pump divided by the mass rate, and then we would have plus VA squared over 2 minus VB squared over 2, And I think that's pretty much all we can do here. So we can just plug in some numbers. So let's write that so we don't miss that. It's HB minus HA is then, what do we got for our pump? Somewhere we said 2 times 10 to the 3. Actually, we'll leave that maybe as joule per second. Maybe just add that here. 2 times 10 to the 3 joule per second, because I think that's going to fit better with the units that we're looking for. All right, so that would be 2 times 10 to the 3 joule per second. That's my W pump. My mass rate we said was 0.684383 kilograms per second. And then plus our VA, which was 10 meters per second, that squared, over 2, minus 25 meters per second squared over 2. And we plug that in the calculator, we get 2,659.84. Just look at the front one here, right? We get joules per kilogram, which is exactly the unit that we want to get for enthalpy. So that's good. And so if we go to kilojoules, and if we round to 3 significant digits, we get 2.66 kilojoule per kilogram. Excellent. That would be our result, right? That would be the change in enthalpy, would be 2.66 kilojoule per kilogram. Now the unit makes sense over here, right? We get it directly. But I think we should just verify real quickly that for the second part, right, for the velocities, we get meters squared over seconds squared. So let's see if we can take that unit, the kilojoules per kilogram, and convert that to meters squared per second squared. So if we just say joule per kilogram, right, then we know a joule is Newton times meters. Just kilogram stays down there. We know a Newton, right? F is equal to m times a, so we have a mass times an acceleration, so meters per second squared, times the meters from our joule. All that's still divided by kilogram. So if we write that more simply, we get kilogram, we get meter, and then we get kilogram second squared. Kilograms cancel out. We get meters squared per second squared, right? So we can see now that meters squared per second squared comes up with the same as joule per kilogram, which looks a little strange, but that's how units work. All right, so this was trying to figure out what the enthalpy change was from A to B, and based on an exhaust system in the middle there somewhere, and we found out that the enthalpy changes by 2.66 kilojoule per kilogram.